Good morning. Let's see. I think I need to start
The
broadcast.
broadcast is now starting. All attendees are in listen-only mode.
Good. Good morning. This is George Laird. Welcome to this little seminar on bolt preload. It's a little bit of a cross between a white paper and a seminar because I think of typically these technical seminars are tips and tricks on how to use FEMAP and Nastran. And this seminar is more of a engineering tutorial. And here's some background. Here's the little white paper. Oh, I should slow down a bit. It's early. It's morning. I'm the presenter today, George Laird, and to answer questions online is also my staff engineer, Adrian Jensen. Are you there? Are you in audio? Oh, technical issues. So he'll log on, but he is in attendance to go ahead and answer questions. Yeah, I think I'm getting through. I think the audio is good. If it's not, you guys can reply via your session and say, well, you can't hear me or there's too much static or something. So if it's all good, I'm going to launch in because it's 8:32 and I try to be quite punctual with these seminars. Okay. So here's the background, and you guys, if you're attending, you've received these notes. And it's introduction, what is bolt preload. I look at this as it's not exactly quite what people think when they go into it. I often get questions whenever I have a bolted joint is people say, well, have you included bolt preload into the analysis? And my standard response is, of course not. It's not needed. And usually, 90% of the time that's true. It's not needed. The key advantage of bolt preload is that you're able to capture. Okay, that's what I'm afraid of. Somebody's saying I'm getting an echo effect. Who else is getting an echo effect? Because the way I'm setting this up, it's on a headset. And I can switch over and I can dial in on the regular phone number. Adrian, how's your connection?
For me, it's a little grainy, but it was grainy even before.
Even before? So I think it's just the technology coming through. Okay, I'm going to go ahead and continue. The main advantage of a bolt preload is the ability to do a fatigue prediction on your bolted joint. Yes, structurally we know that a bolt preload will hold the flanges together. It creates a lock on the joint due to friction. But in the modeling world, I often don't like to assume that a joint will stay frictionally locked. I like to run it without friction, clamp it together, and have any sort of shear load be carried by the bolts. That's the most conservative approximation. And then if you're really setting up a bolted joint with contact, that's carrying you in the ability to carry compression loads across the flange and to capture the tensile load of pulling the bolts apart. So at the end of all this, a bolt preload, what it really does is allow you to make a fatigue prediction on how the bolt's going to behave. But let's get into some of the background on it. This example in the notes, I'm going to leave for people that want to read it later on. I'm going to present my own example. And what this covers here is sort of the setup for a bolt preload. And it shows the various screen picks and how to set it up. And then there's an example of if you have a uniaxial load on your structure, this is a simple plate, a column, and what happens if you have a bending load. And it's pretty self-explanatory. What I want to do is I want to build a model and run it. And this is just a simple 2 plates, and we're going to pull up an angle on this side, and it's 1,000 pounds up in the X direction, 1,000 pounds out to the Z. Okay, we're going to put in a bolt, we're going to load it up, preload it, and look at some of the results. So to add in our bolt, I have a little custom API. Where is it? Spider and bolt all in one. And it allows you can pick the surfaces. And I make sure I got the right surfaces right there. Middle mouse button to roll things around while you're in a dialog box. And you guys may notice that sometimes picking is a little funky because it's the default set to normal. I'm going to hold the Alt key down and right click and set pick to front like that. And when you're in a dialog box, if you hit the right click, it still comes up pick front. So you don't need the Alt key. Sorry about that. Sorry about a little misdirection. Okay, back to the task at hand on the API. We're going to create a new bolt property. So we're going to use something out of the database at Steel, and we're going to make it a 1/4 inch bolt. And what the API does is it'll create your rigid link, and it'll create your bolt. And if you go into the property tree, there's your bolt as it's created. In this model, regions have been defined. If I turn on the highlighter, there's the top region, there's the bottom region, and you have a standard connector, contact, top and bottom. Nothing fancy. This is basic contact setup in FEMAP. And if you're wondering how this is done, we have other tutorials on linear contact. Okay, so we have our bolt, we have contact defined, we have a load. If we were just to run this straight out and have a load set up, these are forces. So no bolt preload has been defined. While it's running, it'll just take a second. I'm going to go ahead. It's too fast. I'm going to turn off the geometry like that. And okay. So this ran through, and it didn't run through the contact. It didn't, and I know that because contact is a geometrically nonlinear analysis, and it didn't do any iterations. It ran it as a straight static analysis. So this shouldn't happen because, of course, this is a presentation and everything should be done. Oh, someone in the audience might have noticed this. Said, "Hey, when you're going through, don't you notice that your contactor is disabled?" Did you guys notice that? I had it, for some reason in the model, I had it disabled. It was probably one of the prior runs before this presentation. So now with the connector enabled, now contact convergence, it's cruising along. Load number 1, contact changes, all done. Go into results. There's deform. Let's turn on. And I have it set to just the axial force on the beam is 4,000. So one of the things to check the model, remember how I said I had 1,000 pounds in the Z direction in plane and 1,000 going up? If we go and look in our little bolt here, we can see the shear force in the bolt is 1,000 pounds. And that's what you'd expect. I'm pulling on it, the shear is 1,000, I expect 1,000. But the axial force is not 1,000. It's just 4,268. And the reason is because you have a little, as it's pulling up, it's pressing down here, and you have sort of a force couple going on. And you can see that a little better if we go ahead. We're going to contour contact pressure. So even though this is bolt preload, you're going to get a little bit of setting up linear contact. And as always, work at the interface. As you know, I've been using blanking a lot. I'll just turn that off. So there's our contact pressure. If I want to see just the top, like that. So I find blanking much faster to use than groups. And if we wanted to check the overall behavior, the von Mises, like that. Simple bending. Done. Okay, now let's go ahead and put in bolt preload. We're going to go back to our load definitions. Bolt preload. That's about it. On this, I know a 1/4 inch bolt, the cross-sectional area is 50, it's 0.050 square inches. So if I wanted to put a 50,000 PSI preload, you could type in 50,000 times the area of the bolt. And then it wants to know what are the elements to apply to preload. And there's lots of ways you could do it. You could do property, type. We only have one beam element. I could do it by type. And what that does, edit load, there's your load definition, 2500, is the force that's being applied to it. And it will create a region up here to where your bolt preload is applied. And now we'll go and run it. So this is just the mechanics. This is just model setup and bolt preload. And it's well defined, and if you can dig around and find it in the FEMAP help. And you notice this is load number 2 right there. I don't know, that's pretty faint for you guys to pick up on this web meeting, but it's load 2. It's already gone through one load, and what that is referring to, it's already done, small model, demo model, is that it has to go through 2 nonlinear iterations, 2 nonlinear solution sequences. The first iteration is just tightening the bolt down. And what NX Nastran is doing in the background is that it's shortening the bolt. It's actually physically shortening, making it smaller. It's applying a displacement to it, and it's compressing the surfaces, the contact surfaces, together. And it's an iterative process. It shortens it, it measures the contact forces, it measures the actual stress in the bolt, I should say the force of the bolt, because that's how it's being applied. And then once it's converged, it exits this solution sequence, and then it applies the load and proceeds again with a completely new sequence. So you have to run 2 complete analyses on bolt preload. Not the fastest process. Okay. So we're back to that form condition. Let's look at contact pressure. And we'll go back to here. And you can see logically now with the bolt preload, the contact pressure has moved up compared to like that. Not a huge change. And you can imagine if you had increased the bolt preload, it would continue to move up closer to around the bolt. The thing I wanted to look at here was the axial force on the bolt. Okay, so here we're at 4,800 with bolt preload, and without bolt preload it's 4,200. Oh, 4,300 without bolt preload, and with bolt preload is 4,800. the axial force, or the stress in your bolt, whenever you're applying bolt preload, it will always be your bolt preload and then some. It's never less than your bolt preload. And this is for fatigue calcs. One of the things you have to factor in is that when you don't have bolt preload, your stress will go in your bolt from 0 when there's no load to the full value of the applied load, and it will cycle back and forth through the whole range. When you do a bolt preload, you chop off that bottom section. You start at the bolt preload and you go up here to like 4,800. And if you wanted to increase the bolt preload, you could just go, where's our load? Right to here. Let's say we wanted to make it 100,000. And we'll just double it. Almost done. Okay. The axial force in the bolt. We started with a bolt preload of 5,000, so now it's 5,700. But the advantage on the fatigue basis is that your cyclic load will go from 5,000 to 5,746. So your alternating stress component is 746. And that is the key advantage of applying a bolt preload. And to hand calc it, it's somewhat rather difficult because it's due to the compliance. And I'm going to show some of the equations and talk some of the background on that. Contact pressure. There. You can see it's moving up a little bit. A whole lot. Okay, let's go back to the presentation. Now the nitty-gritty of what's going on with bolt preload. I suspect a lot of you guys might have seen a bolt preload presentation about how it's put together, but probably never really some theory since your junior year in mechanical engineering for those guys that went through that, suffered through that. The bolt preload, think of it as a fixed displacement load, and don't think about it as forces, as applied forces. Think of it when you're clamping down a bolt, you're applying a fixed constraint, and that's really what you're doing. You're tightening up a bolt. It's a thread. There's a nut on the end. As it's being torqued, you're not actually loading it up with a load cell and pushing on it. It is a fixed displacement load. And in this simple model, we're mimicking what the equations are telling us. The way the equations are derived is that we have a rigid link across the top and a rigid link across the bottom. And this model file will be available at the end of the seminar. What we'll do is we'll upload the seminar movie file along with the model file. So if you want to dig a little deeper and play around with it, you can. And the concept is that you're fixing this surface here with the bolt on the two ends. So you have a fixed displacement. And so when you apply the bolt preload, it compresses the complete assembly. So your bolt, the way that the equations are derived is the equivalency of displacement between your structure and the bolt. And you can probably find this, and I dug this out of Shigley. It's mechanical engineering design. And the equation for your final bolt, total axial force on bolt, it's a ratio of the applied force, P, and the stiffnesses of the bolt and the stiffness of your bolted structure, your KS, plus your bolt preload. So anytime you have a bit of compliance in your structure, KS, your final total axial force on bolts, it's going to be a ratio of the bolt stiffness, the compliance of the structural stiffness, plus the initial bolt preload. Sounds sort of obvious. Sounds, so what? No big deal. And you can work it out for very simple rectangular structures, and you can work through the stiffness equation, which is your area times elastic modulus divided by the length. You can work it out that, okay, so if you have an initial bolt preload of 1,000 and your applied load, your P is 500, your final bolt load is 1,250. You can run the model, put 500 pounds top and bottom, try to pull it apart, and your final bolt axial force will be 1,250. Since it's a model, it's always a little bit off, so we got 1,251. Not a big deal. Okay, on to the next. So this equation right here, works only for when the structure is when it's clamped together. If you exceed that clamping force, then it just goes straight to your applied load, your P. And so that limit is reached. You can rearrange the equations, and you can say that if these are flipped around, that your force between the preloaded parts, Fs, you can take your applied load minus your force initial. So when this goes to 0, that would mean the parts start to separate. So for our example here, rectangular block 1 by 1, those parts actually separate at 2,000 pounds. That's when they pull apart. Now this doesn't seem at first, it doesn't seem that intuitive, because in the prior slide we say, well wait, we're applying a bolt preload of 1,000 pounds. Then the first reaction is, well, it should separate at 1,000 pounds. You should be able to pull it apart at 1,000 pounds. But that is if you're thinking in the force world. When you do a bolt preload, you're cranking it down. You're applying a fixed displacement. Is it, come back here. Is it you're pulling the two parts together with a fixed displacement. You're cranking it down. So your bolt preload, when you actually pull on it, you're pulling on the bolt and you're releasing the releasing the compression here. Now, when you pull on it, it doesn't mean that your bolt force stays at 1,000. That's just what you start with. So when they say, okay, when does it separate? When does your flange start to separate? It separates at 2,000 pounds. But what is going to be your bolt load, your bolt axial force? It's not 1,000 at that point. When you have 2,000 pounds applied load here, remember our equation? 1/2 times 2,000 is 1,000 plus 1,000. Your bolt axial force at separation is 2,000. It's equivalent to the applied load. This is an important concept. Is that as you pull on a structure with a bolt preload, the bolt axial force goes up, or the bolt stress goes up. It doesn't say that. And it keeps going up until it reaches the applied load, the maximum separation load. And it's dependent upon the stiffness of the clamp members. It took us several go-arounds, because we were discussing it here in the office before this was really completely clear how this works on bolt preload. So don't be surprised if at first blush this seems a little bit opaque. So applications. What is this? How does this work in the modeling world? when you're working with a plate structure and you're doing a bolt preload, this actually came up. When you apply a bolt preload to a plate model, well, it does nothing. It does absolutely nothing. Why? Let's go back to our equation. You can see why I spent some time talking about this. It's actually useful. So bolt preload equation on a plate structure, flat plate, the stiffness of the clamp structure. So if you're clamping down, if you're pulling these two plates together in this little model here, if you're pulling it together, there's no deformation in the plate normal to the surface. It's a plate model. There is no deformation. There's no it's a solid plate. Now, somebody might say, "Oh, no. I've seen this effect. I've applied a bolt preload onto a plate model, and I've seen the axial force of the bolt jump up." What you're seeing is this contact stiffness. Remember, we're doing a full contact solution. How does contact work? It applies small springs between the contacting surfaces. So, in your contact algorithm, you do have compliance. Now you can override this and make your contact very stiff. And when you do that, then of course your bolt axial force is going to stay the same. It's not going to increase because there's no compliance. And what that refers to is this equation here. If your stiffness of your structure is infinite, if your Ks is infinite, then this value, that equation, goes out right there. Nothing happens. And of course, this equation here cancels out because it's not relevant, because there's no stiffness. So your force of separation this doesn't apply, because what is going on in this case, since this goes to 1 right here, because infinity over infinity is 1. So your force of separation for a plate model is whatever your applied preload to the bolt. That's it. But that's not the reality. That is not the way real structures work. Okay. Now I have a dilemma. I started drawing on this, and now I have to go back to my web meeting software and try to figure. Yeah, I'm clicking. Adrian's like, come on, you just click right there. Huh? Oh, I hit escape. Okay. Erase all drawings. Normal pen. Good. Okay. So you're not able to access what's going to be your alternating stress component in a plate model using bolt preload. What do you get from using bolt preload on a plate model? Well, if you're really trying to finesse it, you're wanting to look at shear effects and frictional effects between your plate model, okay, you could apply a bolt preload and try to get a handle on that. But boy, those are very tricky things to do to get out of a contact algorithm, to get an idea of what the frictional lock is going to be. So it's sort of a marginal effect. So for plate structures, bolt preload, as far as I can figure out, is not needed. And we actually ran a couple models with bolt preload and was, working on it. And they were large models, and we just doubled our solution time because of that. Okay, where is it relevant? Solid models. And this is another example of, okay, you have a solid model, you have compliance. Now you do actually have stiffness now of the contacting surfaces, and the values do scale then. So what we're doing with these simple models is that we're pulling them apart with 50% of the load, 100% of the load, and 150% of the bolt preload. And at 50%, the bolt preload is set to 1,000. And if we apply 1,000 pounds of force, this is 100, the bolt preload goes up to 1,285. And because remember, what's going on is that it's a fixed displacement when we torque it down. So we're squeezing together both structures and the bolt. And to pull it apart, you got to come over the effects of the bolt, the complete stiffness of the structure of the bolt, and the compressed material. And then, of course, it's exceeded when you go to 150% of the bolt preload. It goes up to 1542. This is a rather short seminar. There's not a whole lot of material that I can go over and and say this and say that, and different examples. I would say really the best way to get this to a really good comfort level is that you just have to build some models and play with it and prove it to yourself. And that's where we ended up going with this is that we just had to build a really stupid, simple model like this and validate it against theory just to get our minds around it. And then take it to some place that doesn't seem entirely logical, like this plate model. It's logical now, of course, but when you're first looking at it. And then the real world scenario where you're actually compressing something together. With respect to fatigue, this is what we're referring to. If you look at a standard simple Soderberg equation, and where we're taking into effect some mean stress. And if you exceed 1, you fail. If you're under 1, you're good to go. And this is just a very simple, fails, passes. And if you take our model and put in some engineered values on it, the alternate, if we run through this example and we say, and this is worthwhile, is that we're using just our simple block. We'll assume that any external load increases the bolt preload by 20%. Bolt area 1 square inch, bolt preload 80,000 pounds. Alternating stress, externally applied load is 100,000 pounds in our little chunk. This cycles from 0. So it goes from 0 to 100,000 pounds. Standard cyclic load, like that. I should start like that. Let's be fair about this. And this is our 100,000 up there. The bolt endurance stress is 70,000, and the yield is 140. And this is just the real classic. If you actually had number of cycles, and you had your stress over here, the virtual whiteboard. And this was your yield at 1. This would be your ratio. God, it gets a little harder at times. Call this our yield. You get your nice little fatigue curve like this. This is for steel, so it's going to flatten out. And sorry about my drawing. It's not quite. This is 0.5. Boy. Okay. So if we put in these numbers and our alternating stress, so the bolt preload is set up. Where is this is with no bolt preload. Sorry, I'm almost done. Our load is 50,000. Our load is 100,000. Our alternating stress then is 50,000. Our mean stress is 50,000. So if I run this through like this, okay, there is our mean stress. Right in between. Okay. Our alternating stress is the complete range divided by 2. You guys are probably going, oh yeah, this is like obvious. Okay. So if you put this together, then of course you're going to fail because this is our example. And then in bolt preload, the axial force on the bolt, and our bolt area is 1 square inch, so we keep it simple, is 0.2 times the applied load. So this is our P from the equation. And this is our bolt force initial, because we're doing a bolt preload of 80,000. So F of B is 100,000. That is the final load on the bolt. Now remember, we're going, in this case, our load, it's going from 80,000 here. This is with no load being applied. What does this do? 80. And it's peaking to 100. I want you guys to know I'm actually writing with my right hand because of my mouse and I'm left-handed. I don't feel so bad. So this, the in-between, of course, is 90 is your medium stress, but your alternating stress is only 20,000 divided by 2. So with your bolt preload applied, the bolt passes. This is the main advantage of bolt preload. If you have to get in and do detailed bolt fatigue calculations, it allows you to make very accurate predictions on what's going on. So, but if you don't have to do bolt preload, if you don't have to do detailed bolt fatigue calcs, it's hard to say from my viewpoint, well, how useful bolt preload is for analysis technique. Because, let's see if I can get out of here, normal, non-drawing mode, into slideshow. Because at the end of the day, you're having to run 2 iterations on your model. And most engineering models are in hundreds of thousands of nodes. And if you have to run 2 complete geometrically nonlinear analysis, instead of being a half hour, it can be an hour. And so things start to slow down. So that closes out the seminar. That's all I wanted to say. Hey, if you guys out there in the audience, if you found applications where you say, oh boy, bolt preload really changed everything, made it perfect. We really weren't using it for fatigue calcs. It was doing something else. I'd like to hear about it. And I'll try to put if I get comments back when I send out the summary of this seminar, along the link with the model notes and other things. I'll include those comments in my responses. So Adrian, any comments should I bring up? Any other questions? Might be general interest?
No, I think that covers everything. When I was going through this yesterday, I took a few notes, and the big key points you really covered. For infinitely stiff structures, the force required for separation is just the preload. And again, those are the plate models that we're talking about, infinitely stiff in terms of compression.
Yeah.
Also, for real structures or solid structures where you do have stiffness that's not infinite, the force in the bolt is always greater than the applied load until separation. And that was one of those things that we talked about. It was difficult to, it was almost counterintuitive. How can we pull on our little block 2,000 pounds until separation? We only have 1,000 pounds of preload. The preload always increases with the applied load. So those are the 2 things that really clicked for me, and I thought I'd kind of reiterate. As far as questions, we only really had one question, and it was asking about our Bolt API, and I believe we have that one on the website.
Yes, we do.
And yeah, we can. You can go ahead and download it. It's pretty self-explanatory. It's a nice little thing. Creates your rigid links, creates the beam element, creates the property if you want to. And yeah, that and all the other APIs are available on the website under resources, downloads.
Right, and we are available if you out there in the audience, if you come across things and you'd like a little API written that would really help on your cut down on the repetitive work. We're glad to help out. That's part of technical support. And then, of course, people, where do a lot of these APIs come from on our website? Well, they come from you guys. They come from client requests. And so the spider boat was part of that request. Okay, well, I'm going to shut it down. Thank you very much for attending, and have a good week. Bye-bye.